Yes, thank you, Steve. And I'm
These lights down a little bit.
Oh, yeah.
to be here. And so basically to give you an overview of my talk, that's to basically motivate it that for me, quantum gravity is the aim to understand really what is quantum space-time, as also discussed Carlo. So I will have a very short motivation because it was already motivated a lot. What we have to face is to how to do quantum field theory without space-time. And then it's basically the question, how can we decode quantum space-time in getting observables and the algebra. And the last point is, so this will be extended comments probably to Don's talk. This will basically pick up what Carlo talked to you about the boundary formalism. And here we will also discuss basically what does it actually mean to have infrared and UV, because that is the title of the workshop. So I thought maybe we should discuss this. Yes?
By doing quantum field theory without space-time, do you mean without just a metric and keeping a manifold?
Without the manifold, basically. But it will come here, maybe, the motivation. So we are very used to perturbative quantum field theory because it's a huge success. But what we have here is basically a fixed notion of space and time, of course. And we have this great idea that we can kind of localize interactions. Of course, we don't really localize interactions. What we ask is that the particles or the excitations are far, far away. Now, if you think about it, how is far, far away defined? That, of course, includes a background metric. And what we usually have is also just the Hilbert space for the free theory. We don't need to care about the Hilbert space here if you do perturbations. However, I mean, perturbative quantum gravity has its uses, but it doesn't give you an answer of what is quantum gravity over all scales. And probably I think also that, important questions like the Big Bang, I find it difficult to answer in a completely perturbative.
So, Bianca, I'm not sure I understand the meaning of this sentence with the red no in it. In ordinary quantum field theory, there is such a Hilbert space. Are you saying there are some purposes for which you don't need it?
Yeah, you usually don't construct it. You don't construct the Hilbert space, which includes
something called the Whiteman reconstruction theorem.
Yeah, which in principle
functions, and Whiteman taught us that we can reconstruct the
Hilbert space.
Hilbert space.
Yeah. Okay, I agree, but then usually it's not done.
Okay.
I mean, it's basically the question that if you really want to have the non-perturbative vacuum, that's very hard and it's very far away from the perturbative. I mean, it's a different Hilbert space.
Sure.
From this one.
But you're not questioning that there is a Hilbert space. You're just saying that it may be hard to.
It's usually hard to. Yeah. It's usually
in
that
lattice theories in finite volume, we construct that Hilbert space very explicit and non-perturbative.
And I had a slice, if it would be another talk, I have a slice on this, saying this. Yeah, indeed. Then I make the connection that you should do loop quantum gravity, but it's just to show you the difference. So, and quantum gravity is basically then very hard to localize interaction. And also, we don't really know what is space and what is time. It could fluctuate. What does it mean? We have to worry about diffeomorphism invariance. And one of the main subjects is that the things we are used to in all the other quantum field theories, basically these local field observables are not observables of the theory. And indeed, it's very much, you can draw the conclusion already here, but it's basically that what I want to argue for, it basically means that space-times do not exist in a sense, but need to be reconstructed, but probably you can only reconstruct that approximately. Okay. And the main question then also is there some notion of a Hilbert space supporting diffeomorphism invariant excitations? So another motivation is, since many people here seem to be motivated and doing entanglement between regions, Now, that's absolutely not well defined. So if you just think, here is a region with coordinates, and here's a region with coordinates, compute the entanglement there in gravity. So there's a big question of how to compute it. And there's a suggestion, basically, and it's also discussed by Steve, that you actually should look at the observable algebra and think about the splitting of observable algebra. So maybe that motivates really the question, can you obtain something like local field observables from gauge invariant observable algebras? Okay, so basically, in this sense, I see as a quantum gravity aim to basically have this Hilbert space supporting diffeomorphism invariant excitations. And such a Hilbert space should, of course, carry a representation of the diffeomorphism invariant algebra of observables. So just that everyone is on the same page, I will, in the basically now the second part of the talk, more talk about the canonical formulation. So gauge invariant observables, I guess you all know what it is in the covariant picture, just things which are invariant under diffeomorphisms. That translates due to Dirac, which we had on Monday, to basically functional of the phase space variables, which Poisson commute or commute with the constraints of your theory. And they only need to commute weakly, which means on the constrained hypersurface. Now it also commutes with the Hamiltonian constraints, so they are constants of motion. Unfortunately, there's usually, I don't know how to call it, confusion in the literature, that there are still coming up claims that these observables are not equivalent. So I would just claim that they are the same, and probably for some parts it's obvious, but for other people they still claim that.
For the classical case, or
for the I mean, so on a trivial level they are the same, and then there are of course lots of subtleties. But it's just that if you already claim on a trivial level they are not the same, you never come to the subtleties, which will be one of the slides. And so one difference then is that there's a result which basically derives from that the observables are constants of motion. And so you can ask, how do they look like if you really try to express them as phase-space functions? And so that's an important point to keep in mind. And you can show that, indeed, any observable needs to include infinitely high-order spatial derivatives. And the result actually just says that there are no hidden symmetries. Actually, it's proven by showing that there are no hidden symmetries. And so this tells you actually that you need to kind of solve the theory, which we will come by in a minute. So here it's just maybe this point of fake versus real problems. So we say that observables have to be constants in motion, and so that leads to the frozen time problem and no evolution. And it's very scary because you have endless winter.
I was a little bothered when you said that. I mean, we know that in certain cases, asymptotically flat boundary conditions or asymptotically ADS, the Hamiltonian is not just the constraint, right? The
No, then
there's still surface terms, and there can still be non-trivial dynamics.
So let's, for the sake of this discussion, let's say compact spacetimes.
Okay.
But in principle, we can discuss that later. Yeah. I mean, of course, there's this asymptotic boundaries conditions. Okay, so that you can resolve by, as Carlo mentioned, and I will explain, by choosing a part of the system which serves as clocks, and you express evolution with respect to these clocks. And so now the real question, maybe, which you should worry, is, are there perfect clocks? And, I'm actually a fan of this picture. I think Carlo is too, and maybe other people are too, because from this you can draw an interesting conclusion where the idea of the argument is that we can't measure certain things, so certain things don't need to exist in our theory. And 3 gentlemen in this audience have a paper on that, and there's basically few people which are working on this, and I find it a very interesting direction to explore. Then you could also say, okay, maybe we have to add such clocks, and people are kind of, maybe to a different degree, very open to say what is actually going on. So Ted actually called it ether, because it's kind of an ether. So then now there's basically a large number of works which go in this direction. Probably Kukash was one which maybe started it most actively at some point. And this is very much related actually to the question, should you treat time symmetry, so the kind of time reparametrization inside your diffeomorphism symmetry, should you really treat it as a gauge symmetry? And Kukash, for instance, for some time said no, but he was not really offering a resolution as far as I could say. Hojava said yes, but actually with a different motivation, because the main motivation was renormalizability. Interestingly for me is that basically this ether stuff and the Hojava stuff might be related, as Ted might tell you, or Anthony. So basically there is this conclusion, if you really can't live with perfect clocks and introduce them, you end up actually with a different quantum theory. If you are more in this camp, maybe there are no perfect clocks, then there are a couple of things you need to worry about and discuss. And here there are just some citations. I'm basically going to discuss these more in more detail. Basically, the question is always what happens with quantum fluctuations with clock time going backwards. Okay. And so the real problem usually is the non-existence of perfect clocks. It actually just means, it's a problem more in quantum theory, because the problem is that quantization requires control usually over global features in phase space and space-time. So here, basically just the definition of these relational observables, which we had shortly, and they were also coined complete observables by Carlo. So the idea is simple, is basically if we actually measure the position of particle, we always do it at a certain time. So we just say, if really time is one variable of the system, we get an invariant observable if we asked, where is the particle at that moment in time when the clock t shows the value tau? And you already see that this, is kind of has a flavor of a prediction. So we actually need to solve really the dynamics to answer this question. So if you have many constraints, or if you have many field series, so instead of one clock, you need to introduce many clocks, and so you need to roughly introduce one clock per constraint you have, or one clock per gauge symmetry. This introduces something which you could say has some analogies with a quantum theory measurement problem. So it's a gravitational measurement problem. In this case, you have to divide your system into an observed subsystem and clocks and rods. And sometimes what is forgotten is actually also conjugated momenta. And so let's go on with these complete observables. So again, for some reason, there was somehow an understanding that these things don't exist for some reason, so it kind of helped to have an explicit expression for these complete observables. So here it is. It's a series expression, so that gives you just the complete observable choosing a number of clocks.
Is this kind of similar to the observable that Don wrote down?
Yeah, it's the same. It's the same. Yeah. So I come to this point. Yeah, maybe not. It's basically the same observable which you wrote down covariantly, and this is basically just the same thing expressed in phase space. There's a subtle. So maybe here you see a bit slightly more detail where there's a subtle detail, which is this small -1, which you can't see, so that's good. So this is the most important detail, because this matrix tells you how good are the clocks. It's basically, how fast are the clocks with respect to the constraints. And this -1 is basically the main problem usually in quantization in this sense. If this is a non-trivial matrix, then that's where actually lots of non-trivial things come on.
But you know that this matrix doesn't have 0 eigenvalues, right?
That's, you have to choose your clocks conjugated to your constraints. I mean, and I tell you, you all know these in different forms. It's always the same thing. It's just that people claim it's different. In any case, what can you do? So the other thing, you see that it's basically solving the theory because this is just time evolution written in a funny form. So here you have a Taylor series. So just.
Excuse me.
Yeah.
Are the clocks made out of protons, neutrons, and electrons?
Are
they some kind of completely different field?
I come to this point on the two or next slide. Next slide.
Next.
Or next to the after one. So what could you do with this? What I will speak now is that actually, so these are really like Heisenberg observables. So you are not really, you started with a fixed hypersurface, but it means you have now constructed gauge invariant variables. And so these actually are space-time or Heisenberg operators. So actually these are just Heisenberg operators. So what you can actually immediately compute are space-time commutators. And so this is an awful object, but it can be used to develop approximation schemes around a background or a symmetry-reduced sector and cosmology and so on.
Bianca, before you go on, remind me, the tau there should be thought of as...
Also, yeah, I didn't really explain anything about this.
But is this the reading on the clock, or is it normalized to be a proper time?
So tau is a reading of a clock. Sorry, I didn't mention that. T are the phase space thingies, so the phase space functionals. Sigma I use for the spatial hypersurface. So that the sigma is completely lose their meaning if in this context. And so these are these constraints which I managed to render weakly commuting by this trick. And so the point is that if you check what's happening here is that now these new constraints are really weakly conjugated to the clocks. And that was a technical point because one argument I heard from somebody which happened to be my supervisor is that this can never work because the constraints are non-commuting. So okay, here is to say that all these different things which you might know in different forms are the same, which basically Don said. So basically this framework, it matches also in some other aspects the Poisson brackets I mentioned, and actually generalizes lots of other things. One is gauge fixings. So what is meant by that is you can do a gauge fixing or in phase space, but you can easily define now if it's a perfect gauge fixing, you can define a gauge invariant extension. So then you get a function, phase space function, which indeed is invariant. So that's the same, and it's kind of an exercise in this book. And the other thing it's also generalizing is basically deparametrization and reduced phase space in a sense that here you really gauge fix and don't care about the gauge invariant extensions. And here so it allows all kinds of clocks. I say it can be any phase space functions which you choose. It just needs to be reasonably good with respect to the constraints. So intrinsic, extrinsic, non-local, geodesic, GPS, cosmological time, whatever you have in mind. And even this cosmological time, things which are not very obvious, because cosmological time would be something like proper time of a geodesic from a Big Bang to your point where you are, which might not be the best thing if you want to resolve a Big Bang to use. Okay. And so basically, classically, it also allows a full reconstruction of space-time in the sense that you also get lapse and shift and so on. Okay, let's come more to the non-formal stuff, which is how do you recover these local quantum field observables, at least in some limit. So you have a background, and you say, okay, I want to consider perturbations around this background. And I want to kind of get my standard observables from quantum field theory on curved spacetime. So then, of course, if you can't choose clocks which are everywhere perfect, choose clocks which are at least very good around this background. And so what do you get? And so let's choose Minkowski space. So to say first, if you want to do this expansion, so there's a nice thing about this framework is that it can be easily expanded in perturbation theory, and you can make sense out of observables up to a certain order in perturbation theory, and also constraints up to a certain order in perturbation theory, and so on. So you define this everything up to nth order in perturbation theory. So then you can find clocks which are conjugated to, say, the linear part of the constraints. So you can basically change that. And actually, I didn't need to do that because for Minkowski space, this is exactly what EDM wrote down at some point in their paper on EDM, whatever stuff. So this actually defines EDM gauge. And there's an interpretation, because you might complain now, this really looks very canonical. But what you get here is an interpretation which also EDM already had, which is that you now express a metric in a coordinate system which is as much Cartesian as you can basically achieve. So that's basically space-time interpretation of these clocks. So the advantage is that these clocks, they don't need any energy or they don't need any mass to be good clocks. So it's similar to Don's remark about harmonic gauge, and you can also put harmonic gauge here with some details, modulo some detail, because that's in here. So with respect to this background, on this to lowest order in perturbation theory, they are perfect clocks because they always go forward. That's advantage. The disadvantage is, they look like this.
I'm slightly confused. So you're building these out of some of the fields of the theory? Or?
Yeah.
Okay.
Yeah. So it's these are the clocks.
Yeah.
I mean, there's an explicit expression.
So the fields with like a classical background, like the kinds of things again that Don was discussing, or different?
So here you can in principle define everything in the full theory.
Is it what?
In the full theory,
yeah,
but what you do is to split your metric in Minkowski plus perturbation.
Okay. I'm just wondering, for example, if you're using a classical background to localize with respect to, then you do have, the energy of the classical background, for example.
Yeah, so that's an energy of Minkowski, whatever that is.
Well, sorry, you've got other fields besides the metric, or?
You could do that with
classical background.
You can do that without any other fields.
Just the metric.
You can do, but I will discuss the scalar field. Yeah.
I'm embarrassed to ask this question, but could you define what a clock is?
Yeah, sorry,
a physical system that does what?
So a clock is a phase-space function.
A phase-space function.
Any phase-space function.
A clock on the wall, a phase-space function.
Yeah, but a phase-space function which needs to, at least in a certain phase-space region to be a reasonable clock in that the commutator with the constraints does not vanish.
Doesn't it keep track of some time? And what time is that?
Yeah, so here it is reconstructing this Cartesian coordinate system, this maximal Cartesian coordinate system, which indeed at infinity, if you run Minkowski, gives you the time at infinity, for instance. But you can also take a scalar field, then it's a scalar field dust, as a scalar field clock.
Keeps track of a scalar field?
Yeah, it's the value of the scalar field which you use as clock. That's what Don discussed.
Bianca, does this work, for example, for inside the horizon?
It's perturbation theory, so I'm not sure. I mean, the point is here, it's you want to reconstruct the standard observables to some order. And of course, they will fail at some point. Okay? I mean, that's a problem. There are no perfect clocks. I mean, that if you don't do something artificial, which I will come to, then there are no perfect clocks in general relativity.
So I'm still hung up on what maybe I'm just confused about a point. Say you just mentioned using a scalar field clock, but you've got this comment: clocks don't need energy mass to be good clocks. Now, certainly, if you use a scalar field clock, it's got some energy, and that's part of how it's evolving and gives you, in some approximation, a good clock. So I'm just. Are you saying there's another kind of clock that doesn't have any energy?
So basically, what happens in it's this difference between constraints which are linear in the momenta and which are quadratic in the momenta in some sense. So a scalar field, if you compute the commutator of scalar field with constraint, you get roughly the momenta of the scalar field. So that means if you want to have a fast clock, it needs to have high momenta. Here, what you get to first order is equal to 1. So in this sense, it's a huge difference between things which are equal to 1 or which are equal to the momenta. And I will explain you the difference. It's basically...
Can you explain what you mean by here? I didn't understand what the context was you were discussing. You said here you get 1. What was here?
Here, in this ADM context, I mean, for the ADM clocks, these clocks, if you compute the commutator with the constraints, then to the lowest order in these perturbations, you get 1.
By ADM clock, you basically mean you're measuring proper time in the space-time along the...
Yeah, I mean, okay, so here ADM clocks means you have a global time, which happens to be the one at infinity, and you need lots of local clocks, which tell you how the hypersurface is embedded in your space-time, and you ask questions to this hypersurface, and so on. And it's actually just what you would expect, because here are the clocks. So here you need an inverse Laplacian that makes things very non-local on the first sight. And then there's a linear combination of longitudinal and trace modes of your metric and of your momenta. And so these things, together with the linear constraints, kill you all things except the TT modes. So it's made up out of this L and T modes. And of course, the modes in itself are very non-locally defined. The longitudinal and transverse modes. Okay. So the reason why you choose them, you don't have to choose them, you could choose other things, but in this case it's motivated indeed that they are perfect clocks to lowest order. So what happens is basically that space-time points, they are now labeled by basically tau and sigma, but they really appear as labels of gauge-invariant observables. So you can now compute a family of gauge-invariant observables to any order in perturbation theory, depending on your patients or the students. And these initial labels appear, labels for space-time points label also these gauge-invariant observables. And so you can do that also for cosmological setup where there's a bit of interesting addition that you don't fix a fixed background space-time, but a family of space-times which are homogeneous. And so you have also homogeneous clocks. Okay. What is this? Yeah. So let's consider, you could compute it now with only gravitons, but for the sake of the arguments, consider now coupling a free scalar field. And the point is, as I told you, to compute the space-time algebra. So here are these complete observables with an awful notation. So basically, you compute now these observables, and it's nothing else than basically these Heisenberg observables at 2 different times and at 2 different spatial points. And to lower, what do you get? It's actually just here's the Green's function, which is the same as the commutator function, and Jordan function, whatever you call it, for the scalar field. But there's a small addition here. This is GR. plus higher orders. So higher orders could include everything. So you would start, for instance, to get things quadratic in the scalar fields and so on. Okay, and this thing is the gravitational stressed scalar field propagator, and to this order, it is just the Minkowski space propagator plus a term which you can again explicitly write down. It's perturbation theory, so it looks like a Feynman diagram. In a sense, it's a combination of propagators plus one graviton field. And you have also a space-time integral appearing there. So this is the result to this order, and I usually interpreted this term. No, it's actually something which describes the fluctuation of causal structure away from Minkowski space-time.
But why is that the right interpretation?
Yeah, so what I cannot tell you exactly, what I'm not 100% sure is that it does not vanish outside the light cone.
No, but suppose it doesn't vanish. I mean, I'm not sure whether you intended this to be, you have little squiggly lines, so this looks like a Poisson bracket or a classical calculation.
Yeah, so these are Poisson, yeah.
So if you're just doing, gravity near Minkowski space, where's the fluctuation of light cone? Why wouldn't I just say that this is because, you've defined an observable which is intrinsically, as you said, non-local, so there's some non-local part of the commutator.
So the idea would be that you see that really in the expression for the graviton, because it's really, a scalar field propagating and then a graviton interfering, and so changing kind of the scalar field propagator.
It changes the propagator,
and
but
so
is that changing the causal structure of the space-time, or just the fact that you gravitationally dress the operator and the dressing has some non-local commutator?
Yeah, so idea would be to integrate, to kind of, if you would be in quantum theory, that this graviton field would fluctuate, and so induce, if this graviton field is non-zero, it could basically change, could lead to a non-vanishing result outside the light cone.
But say you're in the classical theory,
Which you are.
Yeah, but the idea is that quantization reproduces the commutators. And so for the free theory, it does. I have to make...
Okay, but...
that is exactly what you get in the quantum field theory.
But there's a Newton's constant in this term, but no h-bar.
No, because, the commutators, if you have a quantum theory, they get all multiplied with an h-bar.
Yeah.
Okay. So the point here is actually that you recover the standard commutators to lowest order, which is, this one. And you get a gravitational dressing. Actually, not only gravitational, because you get also at some point just self-induced self-interaction of the scalar field to higher order. And so in principle, you can express everything in a gauge invariant way to a certain order.
And is there a choice in this gravitational dressing, or is there kind of a unique...
No, it's a computation you do. It's something, you make this... So the choice we have is initially the clocks. So I've chosen here ADM clocks. You can choose other clocks.
Right. When other people, maybe Don most recently, talked about gravitational dressing, they like to put in this particle and then choose the gravitational field going in a particular direction.
Yeah, so then for
this... In that
this...
picture you have some choices.
Yeah, so the clocks are some choices, and the next slide will be, we choose other clocks and see what happens. And I haven't done the Don calculation.
Bianca, has anybody done anything like that? In some practical theory? Like at one loop order, for example?
Not exactly like this. There have been discussions about light cone fluctuations, and then Kafkin said, they are not exact and slightly wrong, and try to improve on that.
Can I just ask before you move on, you referred, did I miss the explanation of what an ADM clock is concretely? I saw an abstract definition, but can you tell us in terms of the metric and how to get momentum? What is it?
So I haven't written the exact expression. It's here, so I can tell you. I have to go to the paper to tell you exactly. So there will be derivatives and explicitly the longitudinal and the transverse modes appearing. And there's some combination of QAB and pi AB, depending on whether you consider the diffeomorphisms or the time clock.
And then
that's a Laplacian.
But these are measuring the time in some specific, the t-coordinate in some specific gauge.
So
is that the idea?
So there's a global time, which is a time at infinity. And additionally, what these clocks do tell you is that you're looking at a question on a hypersurface, which is kind of as straight as possible. And then kind of, you choose coordinates so that these coordinates are as Cartesian as possible.
So in Minkowski space, this agrees with the Cartesian time coordinate.
In Minkowski, exactly, thanks.
And it translates into some gauge condition that you could write down.
And exactly this is done in the same way as in cosmology. Cosmological perturbation theory, it's very similar clocks and similar interpretation.
Sorry, in cosmological perturbation theory, often, again, you use, say, the inflaton as a clock, so you actually have a real evolving scalar.
Yeah. So, then other people use longitudinal gauge. So you could use, for instance, longitudinal gauge or some other gauge.
So that's the problem, yeah.
And you have, however, to use usually global time, which then you can take the homogeneous clock, and then it depends on whether you really want to stay exactly on constant phi surfaces or not. And that makes a difference. Some people, I'm not a cosmologist, but.
What do you mean by ADM gauge? Sorry. ADM was a foliation of space-time without fixing it.
No, sorry. So in this paper, they also discuss linearization of gravity, and they define this ADM gauge.
Okay.
So.
You don't put to zero the sheet or something.
Here you don't need to discuss the shift and lapse. What happens? You take these gauge. It's actually one parameter functions of gauge fixings. And this will define you afterwards what lapse and shift is. So it reconstructs you the full space-time. Yeah.
Well, maybe just one remark. I mean, I've done sort of one-loop calculation where you can actually follow graviton trajectories, and you can show that the presence of a scalar field there is a light cone shift, and it's proportional to g of the order of g. We can discuss this later.
Okay. So let's contrast that with what Don had. I call it the 5 scalar fields idea. So you use 4 scalar fields as clocks and observe a 5th scalar field. And these, they have the advantage that they indeed seem to be much more local, in the sense that you can make an easy argument that they will always Poisson commute if the points they describe are spatially separated. And the argument is that even if you compute them on 2 different hypersurfaces, the entire thing about gauge invariance is that you can evaluate them on any hypersurface you want. And so you choose the one where they are spatially separated, and then all the things there commute. Okay, and so here so there's a slight change of notation. So here we use a scalar field as a clock to compute the Poisson bracket with the constraints. And so what will you get? Because it's p squared, you get a momentum conjugated to the scalar field. And so that happens, of course, for all the standard model, meta model. Model meta. And so you see that the qualities of clock depends on the clock momenta. And so this is basically very similar to what Steve, Don, and Jim have done. If you can kind of try to compute this commutator, and here it's done in this approximation of very nearby 2 points. And so you again get the Green's function between the 2 points in question on a fixed background. But in this case, you get also an additional factor. And it's a more complicated expression, but you can interpret that as 1 plus energy of the field observed divided by the energy of the clock field, where energy is basically some quadratic expression in this commutator, so it's something quadratic to pi squared. So in this sense, you do not really recover the standard local quantum field theory term result because you get this extra term. And actually, so by these three gentlemen, it was used to basically discuss some holographic count on the number of degrees of freedom, because that gives you a bound on how much you can resolve two space-time points. And there's some related, not obviously related, but it's actually the same effect as what you have, is discussions about the time of arrival operator. And so the difference is if you consider basically time as a clock, the complete observable looks like this. It's just a free particle, and you see it's just a solution to the question, what is Q at t equal to tau? And if you ask, what is the time of arrival at the position ρ, then you get this expression. And so here you get also this actually 1 over p of the particle. And this actually avoids it being quantized, so there's an entire book about the problem of how to quantize it. And actually you can derive a nice kind of additional uncertainty relation for this operator, which again is just exactly this due to this term. It's actually really that time can go backwards, that the p can be 0. And so the problem is that you can't turn this into a self-adjoint operator. Okay, so here we have indeed seen an example where you have this difference. You have stuff, constraints which are linear in the momenta, and stuff which is quadratic in the momenta. And Kuka is the one which made a big deal of that. And you see basically this different behavior in the space-time commutators, let's say. And so as an exercise, you can basically try actually takes a free particle and quantize using the position as a clock. Okay, and so there's basically, as I mentioned, you can go around and specially design matter so that you have perfect clocks or better clocks. And typically that means that you try to have something which automatically gives you not something linear in the momenta, but 1. And so one example is the Braun-Kuka-Stas, which was invented by Carlo, apparently. And I just want to say that typically, I don't want to make fun of Carlo, but it's very specially designed matter. So in this case, you assume that every dust particle, you can identify every dust particle. So every dust particle has a name. And also every dust particle carries a clock which measures its proper time. So it's very special matter if you really think of it as microscopic. Of course, again, you can use it in fact for cosmology. You would say indeed, if you go to cosmology, that can be a star or a galaxy and so on. Okay. But there are these comments that if you add stuff and hide it, then you might end up with a different theory. And of course the question is, how realistic are these models? All these clocks then might have some relevance in some regime, but the question is, do ideal clocks exist? I found a remark by Bondi in a nice book about special relativity, where exactly he poses this question, are there clocks which you can accelerate with any bounds? And let's say there's a recent paper which basically says you can't build ideal clocks with quantum fields. And if you really think that if you can't measure something, then the thing doesn't exist, it makes you think about the structure of the theory. Okay. So as I mentioned, there are all these different versions, and probably will lead to more discussions. Yeah.
In prehistoric times, Wigner and Salaker argued that the clocks had to be massive in order to be accurate. They were dealing with ordinary fields. Which of these are you throwing that argument out, or is it incorrect? Or?
I think it still holds, yeah.
Okay.
Yeah.
So therefore, there would be a significant gravitational effect, unless you could take the clock away.
No, maybe, no, indeed, the question is if these RDM clocks, I mean, so the question is, what are real clocks? And what are really the measurements we do, which we already had? And there's a range of opinions, because indeed it's a question, how do we set up a quantum gravity experiment? So maybe it's not so much about astronomical different things, which we can think indeed have lots of ideas how to do that. And I just want to point out that these different opinions lead to very different viewpoints about your theory. So what I want to say is, indeed, you can recover Q of t on a fixed background in a certain as a limit, of course. And for that, it's best to use non-local gravitational clocks in the sense I said. You can use scalar field clocks. And indeed, for instance, Lucien Hardy at PI, he says only these are beables, and I don't care about all these abstract things you can construct. But if you use that, there's a problem that Minkowski doesn't really exist. Minkowski space, in a sense of how he constructed the theory, it's just one point. It doesn't really exist as some extended space. And indeed, the question is, what about vacuum? You have all these dense clocks, so that's the first picture. You have all this field of clocks and scalar fields. Do you really measure, time? Do we do that via measuring scalar fields? Okay, you can use specially designed matter, and ether is one example. So you can ask Ted about this opinion now and then. And other ideas which we discussed already is Carlo had some paper about GPS clocks. So maybe there's a mixture and not filling densely your space, but you just have 4 satellites, I hope. And there's another idea using geodesics. And there was some discussion about the commutators. So let me tell you that there's a recent paper which claims that they commute, which I haven't checked. So, and I'm not sure whether that means that they should commute for all space-like separation. But
wait, sorry. So the paper claims what? Can you say it more clearly?
Okay. So they use kind of a geodesics in one spatial hypersurface to construct coordinates, but they have one special point. And then they say they have a scalar field or a homogeneous scalar field. So they have some global clock maybe, or some scalar field. No, sorry. They have a scalar field for the Hamiltonian constraints. And then you can ask the question, you can construct observables with respect to that. And so I'm not actually sure at which level it is, whether it's before taking care of the scalar field or after that. The claim is that the observables constructed via these things, they commute on this hypersurface. And there are actually 2 papers, because there's a short one where they say, everything is simpler. So there's one, the first paper is more complicated commutators, and the second one is a claim.
So
it's much simpler.
are you just reporting it, or are you? You seem to be sort of suggesting that you don't believe it, but you're not saying that explicitly.
I haven't really studied this paper in detail, so.
I think there's a sort of argument.
I just.
If they're working with one point, you're running GDs outward, then in a spatial hypersurface and only working that hypersurface, then if you choose 2 points, the geodesics run outward from the base point only overlap if they happen to be the same geodesic. So if they don't overlap, then their support is space-like separated community. And if they're the same geodesic, then since they're only using the intrinsic geometry on this, let's call it 3-dimensional surface,
then they commute.
And this Wilson line, if you will, doesn't involve the extrinsic curvature at all, or the derivative of the metric. And so the fact that they overlap, again, you get these things commute.
Yeah, but if you look at any time derivative, if you move off the slice at all, generally you'll get a commutative.
Then things won't commute. But these things, so but if you run a Wilson line out to phi dot, you'll get this commutivity. But yes, the time derivative of a phi run out on a Wilson line with the time derivative of another one will in general not commute due to issues at the origin. There's also the question of exactly what they do to define the point from which they fire out the GD.
Yeah, apparently they want to apply it to spherical reduced stuff. So then it's
Well, there's some issue with choosing the origin, but the rest of it.
Yeah.
Well, and I think because of what was just said, the second line doesn't follow from the first. Observables commute on fixed spatial hypersurfaces.
Yeah, so then maybe that doesn't work.
As soon as you go off a little bit and you're at a generic space-like separation, then they don't commute. Well, or at least in the construction we understand.
So let's say it can be answered, this question. Okay. So this was only a short remark about unitary time evolution, which a priori doesn't make sense because there is no time evolution. And so, in fact, you can use clocks to reconstruct relational time evolution. And that's the point where these exact clocks also are important because only if you have really perfect clocks, you probably can hope that it's kind of unitary in this splitting of two systems. So here's another paper which cared about, actually we never have perfect clocks, so what they discuss is to change clocks if one starts to be bad, and they called it fashionables. And in fact, so that's all in an effective formalism, so you get kind of dissipation effects actually due to non-perfect clocks. So basically just that also unitarity has to be reconstructed, and it's a question whether it can hold exactly.
Is that related to what Gambini and Pullen also talked about?
No, it's different. Because Gambini and Pullen have these non-exact constraints which come from discretization. I don't remember exactly what they do, but it's the initial idea was that
another story regarding imperfection of clocks.
Yeah, I thought so.
Yeah, they had some, but it started with not having exact constraints.
Oh.
I mean, that's a discretization kind of, you get the first step is what you get so-called pseudo constraints. Okay, so maybe the last 5 minutes, which I might have, is to complain about the title of this workshop. Sorry. So, if you're really deep into quantum gravity, the question is, can we define what is UV and what is infrared? And it's something which happens actually to come up in discussions, so it's
with respect to a background.
Yeah. And should it be the other way around? So these are ideas which, is a framework to try to define renormalization in a background-independent framework, and the renormalization depends heavily on the notion of scale. We are in quantum gravity, so we have no idea what scale is. So the question is basically, what do we observe at different scales? And Carlo discussed it. So the idea is to use this generalized boundary formalism, which indeed makes lots of sense in quantum gravity, because a priori the boundary can have any shape, can be a priori, can be arbitrary big, the region you describe, can be small. Everything can happen. And so also the idea is that in the end, dynamics is encoded and the amplitudes are associated to this boundary. Okay. And then here I have some things which look discrete.
Are you thinking about this in a Euclidean signature?
A priori, yes, but maybe a posteriori not, because at least in our models, it happens actually that if you have the Lorentzian models, they sometimes happen to describe all kinds of signatures. So if you are in a Lorentzian model, you can actually write down very weird boundaries where even like a certain boundary is either space-like or time-like. Okay?
Do you claim to know how to interpret the quantities you're computing?
No, I don't claim yet. No. Okay. So even if I have a sphere, it can look anything. Can be a cylinder, can be, I don't know, pancake. So these seemingly discrete things you should not read as discretization, because the number of, say, the lattice here only represents the number of variables you can represent in this Hilbert space. So what you actually have is kind of, in this sense, Hilbert spaces which can only support finite information. But the point is to have an entire family of these Hilbert spaces. So usually what you do, if you now think about lattice theory, that's one lattice that seems to be a coarser lattice in the sense it has less variables. You try to choose a way to coarse-grain your variables. And so actually you would say that this is UV, and this is infrared. And in fact, it makes lots of sense. I mean, you can confirm that by also later on in what I'm telling to say. So then, all these new developments, very exciting in condensed matter, actually tell you that if you want to have the most effective description in how to coarse-grain and how to write your effective theory, you are not free to choose to coarse-grain. Actually, what you try to do, it's a bit complicated. You try to construct a map, an embedding of this Hilbert space, which is a priori smaller, into this bigger Hilbert space. And this map should be chosen such that for the low energy wave function, whatever that means, the UV, which means here less relevant degrees of freedom, decouple from the infrared degrees of freedom. So it makes more sense if you think in terms of partition function, because then it's a question of which degrees of freedom participate in this or contribute to the partition function. So there's a complicated thing, which is that it's kind of a recursive definition if you really want to build it up, because here it uses kind of low energy wave function, which you don't know a priori, and so on. And so that's a problem in designing the algorithms, but people do that. And so you can read this as an embedding. If you read it the other way around, it gives you a dynamically preferred way to coarse-grain your observables, which actually also includes field redefinitions. And so here you have something where infrared and UV degrees of freedom depend on the dynamics of the system. So the splitting of your stuff into infrared and UV, every step depends on the dynamics. And so, in fact, MERA is basically a certain realization of this idea, which gives you a special way to construct these embedding maps. And it does not need to be ADS, actually. It does not need to describe ADS. It can describe anything, especially if you really try to use it for quantum gravity. And so here there's this little point that, in fact, what you do is to try to disentangle your UV degrees of freedom. And the art is then to choose them such that you get the most effective description. Okay. So the last point is, so how to express continuum dynamics. So this basically then is, if you bring it together with ideas of LQG, is that if you want to basically describe your full theory, it should be a family of boundary amplitudes, which are defined on Hilbert spaces on different sizes. And so if you are here on the left, you have only very few observables. You could naively think, oh, this is UV because that's my fundamental building block. But it's actually the opposite you can claim is the case. This is where you have extracted the degrees of freedom which are most relevant on large scales. And so that would be actually the homogeneous degrees of freedom if everything goes right. And so then you need to construct all these embeddings into higher, larger and larger Hilbert spaces. And the point is that you can do that to infinitely and try to get the refinement limit. And so the dynamics then is defined by a family of these amplitude functions, which are these transition functions, the quantum things to the Hamilton-Jacobi function. And so there's actually a very restrictive condition on this family, which in fact is, if you use these embeddings the other way around, as pullback, what you should get back by basically using this high complexity wave function. If you use a low complexity wave function, or you use a high complexity amplitude but a low complexity boundary wave function, you should get back the same result. So basically that means that it's just the same as an effective action, that it tells you, even if you use low complexity infrared stuff, it should tell you all the results, all the stuff which comes from the higher complexity things. Okay, so that means that it's an effective, it's a family of effective actions, and it's a way to actually have a useful description of your theory in the sense, here you don't need to do anything anymore to really have a reliable result. So that's the main point.
So is the point here that this is a concept of how you could have a theory which at any given scale you specified as a discrete theory,
yeah.
But it's kind of an infinite chain of discrete theories.
Yeah, so this is
can be arbitrarily close to a continuum theory.
Yeah, so this is
prediction.
Yeah, exactly. So this is what is used in loop quantum gravity with a fixed choice of embedding maps. So in principle, it always looks like a lattice theory, but the mathematical definition is actually as a so-called projective. It's an inductive limit of Hilbert spaces or projective limit of configuration spaces. And so the point about these conditions is basically everything which you do on a certain lattice, you get the same answer if you go to a refined lattice. So that means that on a given lattice, you already get the continuum result.
Right, it's like asking a computer programmer what is physics, and they'll say, well, here's what I do. And this is what they do. And if you want an answer to a more refined question, they do more mesh refinement.
Yeah.
And they never have to assume there's a continuum because they're doing discrete computation.
Yeah, no, that's the point.
But you're proposing that somehow this should be done. The thing I'm not quite getting is what's your attitude about this? Are you saying this is the way we should approach quantum gravity, or
that's what I'm saying.
Something you could do? Or?
It's what I'm saying, and that's what is, for instance, it's what is happening also in these tensor network renormalizations, in a different attitude actually, but the idea is that they can use it as a non-perturbative definition of quantum field theory.
But can you really go this way in a unique way? I mean, from
so
the
question,
to the ultraviolet?
So the question indeed.
Usually you have microscopic theory, you integrate out.
So let me first say that this is the definition you want. This is the thing you want to reach.
Right.
So the question is, starting with a microscopic theory, can you kind of try to construct this thing? And the answer is yes. There is kind of a framework which heavily uses these tensor network schemes. The question, and it basically means to solve the theory. So actually, it's good that you can do it in an approximation, and it's not surprising that it's actually easier to get that to certain reliability, so the homogeneous answers, than to get the high energy stuff. Then, in fact, what I'm saying is that a complete theory, if you want to know everything on all scales, it would correspond to a complete family where all these conditions are satisfied. Because that tells you that, indeed, you can, that basically an answer which you get from here is not different if you include more degrees of freedom. And so this is exactly what is actually, in standard in standard language, modulo mapping problems, it corresponds to a complete renormalization trajectory. And here the scale is replaced by complexity parameter. So I just tell you that there's a notion of scale which here is complexity parameter. And so the difference between, say, kinematical LQG is that there's a fixed embedding, and it's not the best dynamically. In a sense, it's actually quite bad dynamically, but you can change these embedding maps, and they might have to change at every kind of complexity degree, which is just the idea that if your theory looks different at different scales, then you have to change something. In conformal field theories, it's actually always the same embedding map, for instance, or in topological field theories. Okay. So this is pretty new work, and that allows you to discuss these things. And indeed, it allows you to maybe think about what are observables at different scales. And so what you want to have is, of course, that you want to have something like space-time geometry, at least on kind of large scales, so low complexity variables. It could also happen that you can start from different things and very different variables, and then you get only at larger scales the space-time metric. And emergent gravity is kind of some idea. The problem is that it's very hard to deal with diffeomorphisms if you start just with some random tensor, some random meta problem. Something similar is happening in spin forms and LQG, and string theory basically maybe it's the same thing. And the thing is that there's also a question: what does it mean that? How do you get the normalization flow of coupling constants? So that needs to be extracted out of the theory, which is slightly non-trivial. And the question is then, how do you design a theory so that space-time geometry and gravity, basically together with diffeomorphisms, indeed emerges as a lower complexity description? Okay. That matches very well with a quote by Einstein, which you can think about whether you believe in it or not, which is basically that the theory tells us what can be observed. So here it's also that the dynamics of the theory should tell us what is UV and infrared. And that's Einstein if you don't recognize him. He's sitting on my windowsills and he's shouting at me always these things. Okay, thank you.
Yeah. So, Bianca, there's a set of ideas that go under the name of holography, and different people mean different things by that. Yeah. But one of the things that, for me at least, has always been included in that is the idea that when I take a region of space-time that's bounded, and we can discuss precisely what I mean by the bound, but that there is a certain number of degrees of freedom, a certain dimension of the Hilbert space associated with that. And in that way of thinking, as I make the spatial size bigger, there are more degrees of freedom associated with it. And what I was not understanding at the end of your talk, you also have these finite dimensional Hilbert spaces, which you seem to be associating with more ultraviolet things. So if
Yeah.
I took some fixed size in space-time, you would somehow, maybe I'm wrong about this, but it sounded like you were saying you could fine-grain that more and more and associate an arbitrarily large dimensional Hilbert space with some fixed region in space.
So let me answer. So the first thing is in fact, I mean, just a small remark that size, again, I mean, doesn't make sense. So here it's complexity.
Well, I think we all agree that size makes sense in some semi-classical limit. So I can ask you.
So here it's really about
but
it's.
I have a causal diamond that has a 4-meter radius and a 10-meter radius, which one has a larger Hilbert
So
space?
it's a full theory. So let me give maybe the real answer, which is that which maybe might have been mentioned. So what actually should be happening is that these embeddings, in a certain sense, only add vacuum degrees of freedom. So in fact, there's kind of if you describe a topological quantum field theory in this way, these embeddings only add, states in one always the same state, which is a vacuum state, and it's a BF
Trivial tensor factor.
Yeah, it's this trivial tensor factor. That's what and so in Ashtika-Lewandowski, it's one choice, which is a squeezed vacuum, and actually recently we have defined the opposite choice, which is the opposite squeezed vacuum. And just to say that indeed it's a question, if you add more and more quantum, UV degrees of freedom, what happens is just that you add just more and more things in a trivial state which don't really matter in a, like in a vacuum state. And basically the problem indeed here, I had this remark that the dynamically preferred embedding in effect should really know what is a vacuum state and add exactly this vacuum state. So these are the preferred embeddings. Yeah.
Make a comment on that? It seems to me what you're saying, which is as you say, holography means all sorts of things to different people. So this in one possible version, it's compatible with what Bianca is saying. With the following observation. At each level of complexity, the Hilbert space associated to that picture can include arbitrarily large geometries, arbitrarily large areas in particular.
At each level.
At each level, because the thing can be larger. If you fix the area, the total area, in some complex sense, then the Hilbert space is finite dimensional. Okay, and in a sense, what we want is that if you fix the total area, the Hilbert space remains finite dimensional. Once you go down, it gets its maximum value, and then it doesn't grow if you increase the complexity. So the extra complexity doesn't add anything in terms of number of states at fixed state.
So the trivial example.
The wave function is a tensor product of something on that finite dimensional Hilbert space and something on all these extra degrees of freedom that you had. There's no entanglement between the two.
So the trivial example is actually BF theory. So you can do that easily for BF theory, which is quantum gravity. I mean, some people think quantum gravity in 3D. And there exactly the same thing happens. And in fact, it has all these fluctuations that, for instance, the inside geometry can be arbitrarily large because it's a squeezed vacuum in the opposite direction. And so there you define this, but at every level the number of physical degrees of freedom is finite. So there's some subtle things going on.
So what you're saying is that these Hilbert spaces you're talking about don't contain only physical degrees of freedom. They've got things that, depending on the context, can completely decouple from all of the physical degrees.
I mean, that is, so there's actually still that these amplitudes satisfy the quantum version of Hamilton-Jacobi equations.
No, because at a given complexity, you can have all possible areas. You think about areas, so that's why I'm talking about. So you can take an arbitrarily large area.
Yeah, so Carlo is making another argument.
That Hilbert space,
Okay, so
you
let's
can have a lot of
discuss.
complexity which you don't have if you go down.
Let's discuss a particular example, namely de Sitter space. Do you assign an infinite or a finite dimensional Hilbert space to the set of physical measurements that can be done in de Sitter space?
I don't know how to connect to here, but I would say fine, just my guts.
But so then this
Then
infinitely high
after some
complexity.
point it trivializes.
Yeah. So in that infinitely high complexity Hilbert space, you would have to say that some finite set is disentangled from all of the rest. Okay.
That's what I expect.
So earlier in your talk, you talked about this getting our definition of variable as a function of clock time, right?
Mm-hmm.
And you said it's not, there's no recurrence problem. Is there any sense?
I claimed you could in principle deal with it.
Okay, but my question is there any sense in which you could define a non-decreasing entropy function or something like that?
It's very much, it's very much related if you have a perfect clock. So if you have a non-decreasing entropy function, it would give you a perfect clock.
Okay.
So this comment was just that it can deal with it. That if you have non-clocks which you know are periodic in a periodic universe, you ask question only about periodic observables.
I mean, for example, you start with a von Neumann definition, and then you rewrite it in your language. Is that possible?
I think it's possible in principle, just not very practical. But
do you have any idea how you do it?
Or no. There's a paper by Carlo, but which is about some classicalization of thermal time. So the question would be, how can one use that? The problem is that in this case, thermal time depends on the quantum states. So
Well, maybe we can discuss in private.
So these tensor networks, people have really taken the limit to the continuum, and at the end we can write down the continuum theory in terms of tensor networks. Is that possible here?
No,
like in this Mera, there are continuous versions of that give rise to a way of parameterizing the vacuum in terms of fields.
Yeah, so what I understood, what has been done in continuous Mera is a similar, it's basically the idea that something discrete does not mean a discretization, but is still finite dimensional excitations. So my understanding is that the states you get in this framework are not extremely well understood yet, because they are not really Fock states or whatever. But and numerically what you do in Mera is, of course, you always, in the simulations, you stop at a certain point. But for conformal field theories, because they are scale invariant, the Mera is already just defined by giving just one of these tensors, and that defines the theory. So so here we can do the same for topological field theories. The difficulty is maybe to have an in-between case, being between topological and conformal, where now you need to really define all the tensors for the different kind of coarse-graining steps, which are now all different. And I don't know if you ask in principle or really sitting down and doing the calculation for quantum gravity. If I would have done that, I would not be here. No, then it would mean you solve the theory. So, but we have a program to do it for spin forms. But the point is first to get these answers to see whether you get anything reasonable, and then to go on. But it will be harder and harder, of course. That is basically just a question of bond dimension. And that's always finite in numerical things.
No, but that's not necessarily true, actually. The continuum turns out to be, again, simpler than the discrete thing. It has some nice features.
Yeah, but yeah, and, I mean, my understanding is that the states you define so far are very peculiar, and it's not really understood how they compare to standard quantum field theory things. I mean, that's my understanding from a year or 2 years ago, and then I haven't followed up. But indeed, one of the projects is to connect, say, to easy examples where you would have a representation of these things in the continuum context.
Any other questions at all? Okay, well, thank you again.